let's have a look at calculus. Danny drives a car. The fuel consumption F of Danny's car depends on the speed of the car C. For one particular journey, F is given by, and we have an equation. What kind of equation? Quadratic equation. Let's not forget that when we have question with the function, it's really about x and y values, yeah? What's the other thing we can have in the question with function? Could be calculus or could be integration, isn't it? Now, what does the x and y represent here? F, that is my y, and that represents fuel consumption. So that's what I'm having here, fuel consumption. And C, that's my x, and that represents the speed. So therefore, that's where we're going to have speed, where F is liters per 10,000 kilometers and C in kilometers per hour, with C is between values 40 and 120. So what do we need to do? Show that there is no difference between fuel consumptions. I'm looking for the value of y, therefore they give me value of x, which in this case is the speed. When Danny's car is traveling at, so that's the speed, and then 110, that's the speed. So we are looking for no difference in value. X given to us, y we are looking for. That is simple, just a substitution. We put 60 in place of, my apologies, that should read C, because in this question x is C. So 0.05 multiplied by 60 to the power of 2 minus 8.5, again instead of C, 60 plus 800. We put that in the calculator, press equal, and we got 470. And then we do the same calculation, but this time we replace C with 110. And again, to the power of 2 minus 8.5, 110 plus 800. And again in calculator, and we get 470. So that is very typical in your question. Very often, part 1, part 2 could be just about finding the x or finding the y when we have the other value. Okay, let's have a look at part 2. So part 2, find an expression for what? A derivative, isn't it? That is the derivative. So they are looking for the derivative of this function, the rate of change. This is another word for derivative of fuel consumption with respect to speed. So we need to derive our f of c function, and let's not forget that is a very simple differentiation because we are going from quadratic into what? Linear, isn't it? So here we know each element is derived separately. When there is no x beside the number, no variable, therefore that goes to 0. When we have x, or in this case c, with the power of 1 or no power, therefore the number that stands beside it is the derivative, and only here we're going to be applying, and that's our very first formula from the table, when we take that power in front and then the power minus 1. What happens with the number that stands in front? So any coefficient here, it crosses over, isn't it? So let's work our derivative. So it is 0.05 will cross over, multiply by 2, because that power goes in the front, multiply by x, and then power minus 1, minus, and here we know is only 8.5. So the only thing to work out here is to put that in the calculator and multiply it. And there we have the full derivative. So like I'm saying, it was really nice and easy part. Let's have a look at next part 3. During part of the journey, the speed c of Danny's car at time t is given by. So here we have another function, and again, in this case, that's my value of y, that's my value of x, isn't it? And that represents speed, while this means what? Time, and time is given in minutes. So here we're going to put number of minutes. And that function is for the time being between 1 and 10 minutes. Okay. Use this and your answer to part A2. So what was my answer to part A2? We had derivative of dc. So let's just remember what was that, 0.1 c minus 8.5. So that to find what? The value of that derivative when t is 7. Now the problem we are having here, that our variable here is not t, is c. But what do we know about c? That's the c. So that means if I am looking, and yes, you can do that as a separate calculation or just in one go. So we are saying 0.1, oh, that's not 1. So 0.1 multiplied by c, and that's what the c is, 78 plus 9 ln, and instead of t, now we are putting 7 to the power of 2 minus, close the bracket, minus 8.5. And all we have to do, put all of that in our calculator, press equal, and to one decimal place we should get 2.8. So again, not that very difficult. Let's have a look at next part. So in part 4, show that the rate of change of the car's speed with respect to time is given by. So here we need to create a derivative of what function c, where t is our variable. And again, what was that function? 78 plus 9 ln t to the power of 2. So again, how do we derive each item separate? Isn't it? We know number will go to 0. And here we're going to apply the formula. Yes, what we can identify, we know 9 will cross over, isn't it? When I'm creating a derivative, so I'm going to have 9. Then when I'm looking at my formulas in the table, when I have ln of x, what do we get in derivative? 1 over x. However, we have here more than just t, isn't it? A very simple rule. Once you see a function, you have to create derivative and there is bracket involved, usually positive. That means a function within a function, because t to the power of 2 in itself, it's a quadratic function. So what does that mean? Chain rule. We are applying a chain rule. So how does it work? We derive it as if it was just ln t, and then we multiply that by the derivative of the bracket. So let's create our derivative. So we know that goes to 0. 9 crosses over, multiply, instead of ln x, we're going to have 1 over, and in our case, our x is t to the power of 2, and that multiplied derivative of the bracket. So if I was to derive that t to the power of 2, what will happen? 2 will go in the front, then I have t, and then the power goes down, so it's a power of 1. And then here we can see that 9 multiplied by 2, that is 18. And then what we have here, don't forget t to the power of 2, that basically means t multiplied by t. So that means that t simplifies with this t. If you're a little bit confused, let me write that as all as a fraction, because that makes it a little bit simpler. There. Every number can be written as a fraction over 1. So we can see t and t simplifies out, and 9 multiplied by 2, that's 18. On the bottom of the fraction, we have t. So indeed, that is the derivative of that function. Okay, and let's have a look at the last part. So use your answer to part A3. So that's just the answer that we were working on before, where we were finding a value of derivative df dc when t is 7, and we found that that value was 2.8. And the part that we just done, meaning a derivative of dc dt, which is 18 over t. Now, two derivatives. Where do I have this type of situation? Chain rule, isn't it? But this is the chain rule that we are building. So we have two derivatives. We know chain rule is about 3 derivatives, isn't it? I take one derivative, I multiply by the second derivative, and that equals the third derivative. That's the idea of the chain rule. So to find what? The rate of change. So derivative of what? The car's fuel consumption with respect to time. So this, we have a description of derivative we are looking for, f with respect to time. So it will be df dt that I'm looking for, and I'm looking for it when t is equal 7. That's the reason why here we have as well, we are using that answer. So how do we build that derivative? Well, the two values that are on the top and the bottom of the fraction, those are the two derivatives that will be multiplied by each other. So two derivatives multiply, and that equal the third derivative. So in our case, we have the number here 2.8 plus, now we have here 18 over, and normally we will have not plus, my apologies, multiply. We will have t, but we are saying we are looking for the value of it when t is 7, so we can replace that with 7. We put that in the calculator, we press equal, and we get 36.5 kilometers. So we can see how the question took us from a simple application of a function, then creating one derivative, another derivative, and then chain rule.